Hi there and welcome to Lecture 8. In this lecture we're going to talk about linear regression models. So as a beginning example, let's consider the following. Let's look at 6 people who were given a math pretest, we're going to call that variable x, and then a 1-month instructional intervention. And then they took a post-test, and their post-test scores, which we'll call y, are recorded below. So you can see our 6 people down here and their associated pretest scores. These are on a scale of 1 to 10. And the associated post-test scores. Now, what do we want to know about these data? Well, there's a few questions that we can ask. First, we might ask, how can I predict the post-test scores directly from the pretest scores? And this is going to involve something called a regression equation. So I want to figure out how can I use their pretest score to predict what their post-test score will be after this intervention. And the other question that I'm going to ask is this. Does this regression equation that I've computed in question 1 represent a real relationship between x and y? Now, as you might guess, this is going to get into some sort of hypothesis testing situation. So that's what we're going to talk about today. So first of all, let's talk about linear regression, the regression equation. So this is what we're going to use to predict the post-test scores y from the pretest scores x. Now you may have seen something like this before. Linear regression is often referred to as finding the line of best fit. And let me do the best I can to show you what I mean by this. So here I've put a scatter plot of those 6 data points. Their x-coordinates are the scores on the pretest, and the y-coordinates are the scores on the post-test. And you can see we've got a fairly linear relationship here. As pretest scores go up, so do the post-test scores. So if we were to fit a single line that was the best fit, it might look something like this. I've got a little red line to play with down here. And I'm just going to guess right now at what this might look like. So it might look something like this. Okay. Now I don't know if that's exactly the line of best fit or not. We'll figure that out in just a second, but that might be a decent start. Now, of course, you might wonder, well, how does one choose the line of best fit? How do we find the line that goes through in the best way? And the way we do it is this. What we consider is if we put this line here, this red line, then that red line represents our best prediction of what the post-test scores y will be for a given pretest score x. Now, of course, there's going to be some error with this prediction. For example, let's consider here at x equals 6. If we go up to where the red line is, the predicted post-test score is about here, which is somewhere in between 8 and 9. But the actual post-test score is up here at 10. So there's some error. And particularly, there's, let me do this a little bit differently. There is this little bit of residual error. And in fact, there's some residual error here. There's a little bit of residual error there. There's some residual error there, as well as there. Every one of these 6 data points falls off of this line of best fit by some positive or negative amount. And so I want to, in a sense, minimize those residuals. I want the line that is going to minimize this residual error across all the points. Now, how I do that and exactly how I work out the equations that I'm about to show you would require us to know some calculus. It's not too difficult, but it's certainly beyond the scope of what's expected in this course. So what I'm going to do is jump to the result of how one does this linear regression. And it's a fairly standard technique. It's called least squares regression. The reason it's called least squares, just to give you a little bit of an indication, is what we do is instead of just taking the residual as it is, you'll notice this residual we might call positive. Well, then if that's the case, then this one is negative, right? They're on opposite sides of the line. If we were to just simply add those residuals up, they would sort of cancel out. So just like when we're computing variance, we don't want the positives and negatives to undo each other. We need to make all these residuals positive. The way we do that is we square them. So in a sense, we're going to find the line that minimizes the squared residual errors. And in a sense, that's called least squares regression. Now, the way it works is this. First of all, we start off with an equation of a line. Now, you might remember from some algebra once upon a time that lines look like, I don't know, there's various forms, mx plus b, a plus bx, those kinds of things. You'll see all kinds of different forms of the line. The form that we're going to use is this form, y equals a plus bx, where a is the intercept and b is the slope. Again, this is not standard, but it's what we're going to go with today. And in order to specify the equation, I simply need to come up with values for this intercept and this slope. I need to come up with numbers. And once I've got those two numbers, I've completely identified what the equation of that line is. So what are those numbers? Well, if we use the method of least squares, as I just described, it turns out that those numbers are exactly these. The fit is as follows. First, we find the slope, b. And the slope is defined as the sum of products, I'll define exactly what I mean by that in a second, divided by the sum of squares for the x variable. Okay? And then once you have the slope, you can find the intercept, a, by simply taking the mean of y and then subtracting b times the mean of x. Okay, so this is something you're going to want to write down. These are the parameters of the best fitting line for these data. So if we are wanting to find the equation of that red line, then all we need to do is go to our data and find those components that build the slope and the intercept. So let's do this. Let's work out the regression equation. So I've recopied the data from the original example down here. Again, 6 data points. X are the pretest scores and Y are the post-test scores. Now the first thing that we're going to do is we're going to find the mean of each of those, the mean of X and the mean of Y. And if we do that, they turn out to be pretty simple in this example. The mean is 4 for X and the mean is 6 for Y. And now what we want to do is, just like when we compute variance, we want to find the deviations from the mean and square them. Okay, so we're going to do that. I'm going to do these one step at a time. We'll find these deviations, and so if we take the deviations for X in this column and the deviations from the mean for Y in this column, we get the following. Again, always check yourself. Make sure these do indeed add up to 0. They always should. Now we are going to square those. We want to find the squared deviations. So we do that. Just remember how this works. We take this deviation and square it, and we get a 9. We take this deviation, square it, we get a 4, etc. So this is nothing new. This is just like computing variance. We're just doing it for 2 variables at one time. In fact, when we do this, we find that the sum of squares for X is equal to 26. Again, just the sum of those squared deviations. And similarly, the sum of squares for Y is 34. Again, just the sum of those squared deviations. Now the new thing, and you might remember from just a few seconds ago, I introduced this notation SP, the sum of products. What is that? What that represents is we're going to take the deviation score for X times the deviation score for Y. So in other words, we're going to make a new column where we find this deviation times this deviation, and then this deviation times this deviation, etc. So let's do that. So I've put up here literally what it is. So if we take -3 times -3, we get a 9. We take -2 times -1, we get a 2. 3 times 2, we get a 6. 2 times 4, we get an 8. And then 0 times -2 and 0 times 0 both result in 0. And what we do is we take the sum of these products, SP, sum of products, and that sum is 25. So these are the raw materials that we need to work out the regression equation. We've got the means, we've got the sum of squares, and we've got the sum of products. Now, once we've done this, we can simply work out the details of the equation. First of all, let's find the slope. We find the slope first. Remember, it is the sum of products divided by the sum of squares for X. And we've got values for that. That's 25 divided by 26. So let's work that out, which as a decimal is about 0.962. So the slope of this line is about 1. It's 0.962. And then once we found the slope, we can then substitute that slope in to the formula to find the intercept. So remember, the intercept A is y bar minus b times x bar, where y bar and x bar are the means respectively. So we'll plug those means in, and that's going to be a mean of 6 minus this new slope that we found times 4. And if we work out what that is, we get an intercept of 2.152. So that tells us that that red line we drew in our scatter plot has this equation. Y equals 2.152 plus 0.962 times x. Okay. So now what do we do with this? Well, remember, one of the goals is that we can use this equation, this regression equation, to predict scores. So we might ask, what is the predicted post-test score if we have a pretest score of 5? Well, now that we've got the regression equation, let me put that up at the top, it becomes as simple as, well, substitute x equals 5 into this equation. So if we do that, then we just simply do the arithmetic. We have 2.152 plus 0.962 times the pretest score of 5. That gives us a predicted post-test score of 6.962, almost 7. Okay. Again, this is a prediction, so of course there's going to be some error with that, but what we have with this equation is an equation that minimizes that error as much as possible. So this is our prediction. Now, the other question that we wanted to ask about these data, beyond being able to use the data to predict new data, is to say, does this regression equation represent a real relationship? What do I mean by that? Well, what I really mean is pretest a significant predictor of post-test? Is there a real relationship between these two quantities? And the way I answer that question might surprise you. It turns out that I use analysis of variance, this old technique that we've been doing all semester long. The way it works is technically slightly different, but the concept is absolutely the same. Here's how it works. Remember, Anova works on the notion of partitioning variance. You take the total variability in something and you partition it into pieces that represent one thing versus pieces that represent another thing. Well, that's really what's happening here. We take our total variability in the y variable, okay, and then we partition it into two sources. We partition it into the variability that is accounted for by the regression equation. That is, it's accounted for by this prediction relationship. And then what's left over, we call the residual variability. Once we find those two variabilities, we do the same thing we would usually do in ANOVA. We compute the F ratio, and then we use that to index whether these differences are substantial or whether they're just due to sampling error. Okay, so let's go through and work out an ANOVA. How do we actually compute this stuff? Well, of course we know how to get total variability in y. That's just SSY. So how do we split it now into these two pieces? Well, the way we do it is we use something that you might be familiar with from other contexts, and that is the correlation coefficient. So the first thing that we need to do is we need to find the correlation coefficient for these data. Now, an easy way to compute correlation from what we've done so far is just to take that SP, that sum of products, and divide by the square root of the SS, X, and Y terms. Okay. Now, again, we've got those values already, so this is not a big deal. Once we find the correlation coefficient, there's a nice thing that we get to use. You may remember from other courses that when you get correlation coefficient R and you square it, that actually tells you how much of the variance of the variability is accounted for by the variable that you're predicting it with, R squared. So let's see how we can use that here. Well, the way we use that here is if we want to know that sum of squares, that variability that's due to the regression equation, we simply take R squared times the total variability, SSY. So once we find this R, and we just use that, we use the square of that as the proportion of variance, SSY, that is accounted for by that regression equation. It's as simple as that. And then, of course, the SS residual is going to be what's left over. You take SSY minus what you found for SS regression. Okay? So that's enough of that. Let's go and actually do it and see how it works. So let's go back to our example. First of all, we need to find the correlation coefficient. Okay? We've already done most of the work. This is not too hard. So we take the sum of products divided by the square root of the sum of squares for X and Y. So that's going to be 25 divided by the square root of 26 times 34. Again, just go back to the previous work that we just did to find those numbers. And what does this turn out to equal? This turns out to equal 0.841. It's a pretty big correlation in this case. So now what do we do with that? Well, we use that, particularly we use the square of that correlation to find SS regression. And we take that square and multiply it by the sum of squares for y. So the sum of squares due to the regression is r squared times SSY, which is going to be 0.841 squared times 34, which turns out to be 24.04. So out of that total variability in y, 34, 24.04 of it is due to the regression equation. In other words, it's accounted for by x, by the pretest scores, which means the rest of it, the 9.96 of it, is residual. So let's do the Anova table. We write the Anova table just like we would in any sort of Anova. We partition our variability into two sources. We've got the source due to the regression equation, the residual, and then I've got total down here. I've already put the total SS here as 34. We just found the regression SS is 24.04. So the rest of this, let's just work it out. Let me change my color real quick. 34 minus 24.04 is going to be 9.96. Okay, let's just, I think I'm doing that right, but let's check it real quick. 34 minus 24.04. Yes, very good. Okay. Now let's talk about degrees of freedom. So something interesting about ANOVAs, you remember that to find degrees of freedom, we did something like take the number of groups minus 1, but that doesn't really apply here. In this case, the degrees of freedom for the regression equation is always 1. Okay, that's just it. It's always 1 in this case. So you don't even have to really think about this. This is just 1, and then the residual is going to be what's left over to make the total degrees of freedom. So what I like to think of it is this: how many observations did I have? Well, I had 6 pairs of observations. So that gives me 5 degrees of freedom total. I've got 1 degree of freedom for the regression equation, which leaves 4 for the residual. So the way I like to think about it is exactly that. I find my total degrees of freedom based on the number of observations minus 1. I have then 1 for my regression equation, which leaves basically n minus 2 for the residual degrees of freedom. And then once I've got SS and DF, I simply do the divisions. So the mean squared for the regression equation is 24.04. For residual mean square, I take 9.96 divided by 4. So we'll do that real quick, and that gives me 2.49. Okay. And then for my F statistic, I just want to take 24.04 divided by 2.49. So let's do that. And that gives us something around 9.65 for an F score. Okay, and that's it. That's the Anova table. The mechanics work exactly the same. The only thing you need to pay attention to is, first of all, how do you compute these? And that's what we just talked about. And then think about the degrees of freedom. Remember that a regression equation itself is always 1 degree of freedom. And then everything else works exactly the same. So what do we do with this? Well, we report it just like this. We would report our F statistic in the usual way. We compute a p-value. I'm not showing that part. You've been doing that all semester. And since this is a reasonably small p-value, we would then say that pretest is a significant predictor of post-test. And so there's that. This is how linear regression works. Now in the next video, we'll talk a little bit more about extending the number of predictors, going up from just 1 to maybe 2, 3, 4 predictors. What happens then? The model building gets more complex, and we'll also talk a little bit more about the Bayesian perspective on linear regression as well. But for now, I just want to get you introduced to the basic mechanics of linear regression. So we use it to predict, and we use it to test for significant relationships between variables. So that's all for this time, and we'll see you next time.